And there we go. All right. So on Monday, we talked about transistors. Okay, we talked about how you can use two N-type transistors, two P-type transistors, and then come up with a NAND gate. At the end of that lecture, I also used NAND gates to create a typical, just a regular OR NOT gate, a AND gate, and did I talk about the OR gate? May not have. Okay, so we can talk about the OR gate today. But the point is, it is possible, okay? And that's why the NAND gate is also known as the quote unquote universal gate, because you can use NAND gates, like a bunch of them, to implement all the other logic operator that you need to work on, okay? So that is kind of the outcome of Monday's class. But what is important of Monday's class, is oh, transistors, real devices, things you can buy, things you can put onto a breadboard. They are the devices inside computers. Okay. So instead of using two N-type transistor and two P-type transistor to implement a single NAND gate, the modern day processors just have a lot of transistors. But the point is, each one is still really just a transistor. Okay, so for today's class, we can look it up. Okay, so we can look up how many transistors are in the Apple M4 chip. Okay, because that's sort of the 28 billion, which sounds like a lot, right? It is a lot, but if we were to put a transistor for every dollar that Elon Musk has, there will be like hundreds of these chips because Elon Musk has a worth of 400 plus billion. Okay. So I want to kind of put things in perspective because I did some research today. What about Fox Corporation, you know, uh, the TV channel, Fox, the entire network? How much is that worth? Okay. 20 something billion. That's it. It's only 20 something billion. Okay, as opposed to 400 billion. That's just one guy. Okay, that's just Elon Musk. Mark Zuckerberg is poor by comparison because he only has 200 something billion dollars of worth. Okay, so I think that really helps to put things in perspective in terms of how much money, how much influence you can expect those, you know the entire Fox network is, I think I did some calculation, it's like 76th, let's call it even 80th, okay, of the worth of one single person, Elon Musk. Okay, all right. Part of why that is important is also because we have to kind of remember who are behind all of these GPTs. Yep. All right. So we are pretty much done with physical states, truth, numbers, and computers. The only thing we haven't really talked about is how do we create a OR gate out of NAND gates. So I'm just going to go over that just a little bit because I think it's kind of interesting to show that. And some of you, if you have already taken discrete math, which has Boolean algebra in it, it is something that you might be able to do on your own. All right. So we'll go ahead and just look at the mathematical derivation. So we will say, okay, I want to compute A or B. Okay. Then you go like, okay, A or B is the negation of the negation of A or B. Okay. Double negation cancels out. Okay. Okay, so we go like, okay, that's kind of cool. So the next step is a little bit harder because the next step involves the use of De Morgan's law, which we'll kind of touch on later in this class, but it's not like super crucial in this class. So this turns out to be the same thing as the negation of A and the negation of B. that okay? So you go like, wait, hold on a second here, Tech. I recognize NAND because this negation is negating this AND over here. So that's NAND right there. Okay, you're absolutely correct. So this is basically not A, NAND, not B. So now we go like, but how do we take care of not A? Okay, well, from the previous class, we know how to take care of this because not A is really just A NAND itself. So there we go. This is OR. It uses three NAND gates, but you end up with a OR gate. It computes A or B. Are we okay with this? Are we okay because you are trusting me that I will give you the correct answer all the time? Or are you okay because, okay, I understand the general way of doing this. I can derive this and verify my derivation. Which way is it? Sorry, the latter? Okay, okay. So let's check out the math, okay? So what we'll do is we are going to spell out NAND in its full glory, which is A NAND A is the negation of A and A. And then B NAND B is the negation of B and B. And then the outside NAND, which is this one here, is really the negation of this thing and the other one. Okay, so now the question is, can you evaluate this expression on the last line for every combination of values of A and B? There are four of those. So if all four rows match what you expect from OR, then the expression works out. If it does not, then TAC just made a mistake somewhere. All right? So these are the things we can do, okay, just based on what you have learned already. The trick of using a truth table is probably new to most of you, but it's going to be a very useful tool, not only for this class, but also for CISP 440. If you have gone through CISP 440 already, and your professor did not mention anything about truth table, you just got shortchanged. All right, so that's that. Today's lab has to do with cranking out some other gates based on the NAND gate. So I'm not going to spend too much time to talk about today's lab. Instead, I am moving on to base conversion, which is this module over here. Okay, and all of these modules, the ones that I'm talking about or the ones that I have already talked about, the knowledge of all of these modules are already in ChatGPT. So you can actually ask ChatGPT and go like, give me a summary of module 0282. It would do it. Okay. So that's one way to use that as a resource, okay, for this class. All right. So we're going to talk about base conversion, but instead of talking about base conversion, I will talk about several things that you guys go like, why are you talking about this? Okay. So first thing first. First thing is the question of what exactly is this? You go like, okay, let's make it a little bit more interesting. That. Okay, make it even more interesting. That. Whew, okay. So you go like, okay, this is 10.37, which means we have 1 of 10, none of 1, 3 of 10th, and 7 of 100th. Does that make sense to you? So unless you have already taken a class that talked about base conversion, that would not even be on your radar, which is what I expect. Okay, I do not expect any one of you to know your base conversion prior to this class. So you go like, oh, okay, I can rewrite this as 10 plus 0 plus zero point 0.3 plus zero point 0.07, which then translates to 1 times 10 plus 0 times 1 plus 3 times zero point 0.1 plus 7 times 0.01. Are we still doing okay so far? Okay. And then I can make it even longer, unnecessarily longer. So now I can go like, oh, this is 1 times 10 to the power of 1, plus 0 times 10 to the power of 0, plus 3 times 10 to the power of negative 1. Okay, 10 to the power of negative 1 is 1/10. And you guys already know what this is going to be. 7 times 10 to the power of negative 2. Just like it is important in all of computer science, in this class, right now, are you seeing a pattern? The pattern is, oh, so all the digits in the original number is really just indicating the quantity, the number of a particular power of 10. Are we good with that observation? And on top of that, the power of 10 has to do with the location of the digit. Okay? So remember that observation. Okay? Right now, I'm only talking about things that you already know. And this has nothing to do with base conversion. It has nothing to do with computer science, has nothing to do with binary numbers, but it will connect at some point. All right? But this has everything to do with what a number is. A number is a representation of a quantity. In other words, intrinsically speaking, a number is not a value. A value is not a number. A number is more like the name of a value. So I'm going to give you a really quick example. Okay, so for people who are watching the video, I'm sorry, they cannot really appreciate this part. So how would you describe this quantity? Okay, but since I'm a Cantonese native speaker, I'm gonna say. Okay, that's say in Cantonese, which is the same as this quantity. So now you go like, but Tag, you're wrong. This is for, not say. Okay, who speak another language in this class? Go ahead. What do you speak? Russian. So what is this quantity in Russian? Okay, I cannot reproduce that, so I'm not going to butcher Russian. So it is just a name. A number is a name for a quantity. The quantity itself is abstract. It is just an idea. It is a concept. But in order to communicate with other people, we need a standard, which means, oh, we have to use the same way to represent the quantity. That's why we have language. That's also why we have numbers. Okay. Okay. So this is one thing. The other thing relating to 10.37, 10.37 is if you're working at a store, okay, and somebody just purchased an item that is including tax is $9.63, gave you a $20 bill, and this is the amount that you have to give to the other person as change. Do you know how to do that? Can you work at McDonald's? Okay. And I'm not talking about 1,037 pennies. I can do that too. So can you use the least number of coins and dollar bills for this amount? Well, then you already know more than what you need for base conversion. I will explain that. So in this case, you need one $10 bills. Okay, so I'm going to say one of 10. You need zero of $5 bills. I will skip the $2 bill because they are very uncommon. You will need zero of $1 bills. Okay, whoops, the other way around. And you will need one quarter. Okay, so you need one of the quarters. You will need one dime. So a dime is 10. And then you also need zero of the nickels. And finally, you need two of the pennies. Do you know how complicated this is? Has anyone ever tried to explain the US currency to someone who is not in this country to a foreigner who is not used to the currency of this country. It is not easy because there is no pattern whatsoever when you look at the multiplier to go from one denomination to the next. Okay, let's go ahead and check this out. There are 5 pennies in a nickel, 2 nickels in a dime, 2.5 dimes in a quarter, and then there are 4 quarters in a dollar. And then you back to the five, right? There are 5 $1 bills in a $5 bill, and then you would expect and go like, oh, the next one has to be two. It really is two. And what is the next denomination? 20, not 25. You would expect 25 because it looks like we can have a repeating pattern here, but no, we are not having a repeating pattern here. After the 20, what is the next? 50. Do you see there's no pattern whatsoever? And yet you can work this out without a piece of paper. So that means you already know conversion, base conversion. You guy goes like, but what do you mean by I already know about base conversion? What does this has anything to do with base conversion? So let me give you another amount, which is probably in inches, okay? Because inches, the imperial units, which is ironic, is about fractions, right? So we're gonna use 13.625. Okay, that's measured in inches. So this is 13 and 5/8 of inches. Okay, okay. I go like, yeah, you already know about base conversion because if I give you the following units in inches and I just ask you how many of each I need to represent this quantity, you can figure it out. It might take you a little bit of time to adjust to it, but you will be able to figure it out. So we'll start with something that you don't need, which is a 16th, and then we have an eighth, fourth, half, 1, 2, 4, 8, and the next one you don't need either is a 16th. So let's just say that this is the amount of money you need to make change for. And these are the denomination. We have 16th of a dollar, eighth of a dollar, fourth of a dollar, quarter, half of a dollar, $1 bills, $2 bills, $4 bills, and $16 bills. So can someone tell me how many of the $16 bills I'm going to need? None of them? Okay. So how many of the $8 bills do I need? One. How did you know that? Because 16 is more than 13.625 and 8 is less than or equal to 13.625. That's how we know we need 1 8. Okay? Okay. So after the 8 is done, we have what? 5.625 left. So let's move on. The next one is a $4 bill. How many of those do we need? One of those. And then we got down to the $2 bill. How many of the zero? Okay. How about $1 bills? We need one of those. And then we get to the fractional ones, which is we start with a half-dollar bill. How many do we need here? One of those. Oops. What about the quarter dollars? None. Okay, very good. How do we know we don't need any of those? Because by the time we get here, the amount left is 0.125, which is less than a quarter. It's less than 0.25. That's how we know we don't need a quarter dollar. What about the eighth? We need one of those. And then finally, what about because by this time we already get down to zero. So by the time we get to the 16th, we know that we need zero of those. Is that okay? So sounds a little awkward, right? But you figured it out, right? You kind of go like, oh, okay, I get the general pattern. I can reapply what I know about making change in U.S. currency. Just have to kind of bend the rules a little bit and whatnot. Yep, yep. You guys did a good job. Yep, this is a binary number. This is a binary number. All you need is a point to separate the quantity of whole units compared to the fractional units. The point goes here. In other words, oops, I should use the, uh, I just, I flipped the representation. That is my fault. I'm sorry about that. Totally my fault. Because, going, this doesn't make sense. Of course it does not. Tack, you made a mistake. There we go. There we go. So the top is a binary number. 0, 1, 1, 0, 1.1010 is representing the same quantity that we know of as 13.625 in base 10. That is base conversion. Is that okay? All right. So if I give you a really oddball number in a really kind of oddball base, let's try to figure out its value. So in this way, in this particular case, this is a base 2 number, okay, because each digit can only be a 0 or 1. It is in base 2. So I think, did I use the drunk octopus, as an example? Okay, so let's get back to the drunk octopus. So let's just say the drunk octopus says, okay, I owe you this much money in dollars. Okay, you go like, it's in base 7, man. I mean, only drunk octopi would use base 7. So how much do you actually owe me? What should I expect my bank statement to say? So how do you solve this problem? Okay, so let's go back to the base 10 number. Okay, look, go back to this example here. Okay, remember what I said. Each digit in a number tells you the quantity of the power of the base. So this is in base 10. The other thing is in base 7. But the principle works exactly the same way. Every digit tells you the quantity of a power of 7 in the example down there. Okay, so you go like, okay, cool, but what is the power? So now you go like, okay, so the 4 is telling me we have 4 of 7 to the power of what? What is the convention? The rightmost digit without, if you don't have a decimal point, the rightmost digit is called digit 0 because it tells you the quantity of the base raised to the power of 0. So if the 3 is digit 0, the 1 is digit 1, which means it tells you the number of 7 to the power of 1. So that means the 4 is telling you the number of 7 to the power of 2. That is correct. So now we look at this and go like, okay, I think we got this. Okay. So 1 tells me we have 1 of 7 to the power of 1. And then finally the 3 tells me that we have 3 of 7 to the power of 0. That is how we interpret a number in any base. Doesn't matter what base it is. So now we look at this and go like, okay, I think we can figure this out. This is 4 times 49 plus 7 times, no, yeah, times plus 1 single 7, and then plus a 3. 4 times 49 is 196. 96. So this would be 206 then. No, I did not read off my notes. I just did mental math. So can you guys do that kind of mental math? If I give you enough time, you can. Yeah. The point is, if I give you enough time, you can. Yep. Did I make a mistake? Yep. So let's just say that you guys remember what I said earlier, which is do not trust Tech because he did not intentionally try to lie to you. He just makes mistakes. I would make the perfect spy because I can poison information without noticing that I am poisoning information. When the other side interrogates me, it's like, don't hurt me, I'll tell you. and I will pass all the polygraph because I'm actually not lying, but what comes out of my mouth is actually wrong. So where's that secret base? Uh, I think it's over here. And they go like, well, according to the polygraph, he's not lying. Okay, let's go over there. All right. So given that, okay, how do we check that 206 in base 10 is in fact 413 in base 7? How do we go backwards? So you reverse the whole thing, right? So you reverse the whole thing. So now you look at your base 7 and you say, oh, okay, I need to know how many 7 to the power of 2 do we have, which is 49. We need to know how many 7 to the power of 1 do we have, which is 7. And we also need to know how many 7 to the power of 0 do we have, which is a 1. So you reverse the whole process. You say, okay, out of 206, how many 49s do we have? So just mental math. Okay, so the mental math process is to round up the 49 to 50, to be quick and easy. And you go like 4, right? So you go like, okay, there are 4 of those. And then what about the remaining portion? In other words, if I were to subtract 4 times 49 from 206, what do I get? So 4 times 49, sorry, 9 is 196. So this will give me a remainder of 10. So out of the remainder of 10, I need to know how many 7s do we have in there? There's only one. So now we go like, okay, 10 minus 1 times 7 is the remainder, which is a 3. And now we ask, oh, how many ones do we have in the 3? That's an easy one. And now we say 3 times 1, 3 times 1 is 0, so we don't have any fractions. Is the process understood? How to reverse from base 10 back to base 7? It's the same idea as saying, oh, we got some really oddball denomination. We got $1 bills, we got $7 bills, and we got $49 bills. And the change is supposed to be $206. Yes, go ahead. You just need to get a drunk octopus. So are we doing okay so far in the conversion process? Okay. So this is really important, okay? Because even though in computer science as a whole, you really only need to know base 2 to begin with, there are other bases that are really useful too. So why is that the case? Let's just say I want to express 4 billion, okay? As a number. As we already noticed, 4 billion is not really that big of a number anymore because the net worth of Elon Musk is 400 billion. So 4 billion is not even that big of a number. So to write 4 billion in base 10, how many digits do we need altogether? Not that many. Okay, so quick trick. 1 kilo is 3 zeros. 1 million is 6 zeros. 1 billion is 9 zeros. And then you need a 4, right? So altogether, 10 digits would do it. Okay. How many digits in base 2 do you think we need to express the quantity of 4 billion? Nope, not 5 times. There's a rough way to do the conversion. Okay. So the rough way to do the conversion is like this. We look at 1000 in base 10 and we say it is about 1024. We go like, what is so special about 1024? That is 2 to the power of 10. Exactly. And 1000 is 10 to the power of 3. So now we look at this and go like, oh, so if I just need to approximate, then we can say for every 3 decimal digits, we need 10 binary digits. It's not exact, okay? There are boundary cases where it doesn't work out exactly that way, but for estimate purposes, it works out. So 4 billion has 9 zeros in it, right? So it has three of these. So that means we need 30 digits just for the billion part. 4 itself is 100 in base 2, so that's three more digits. So that means 4 billion is going to need about 33 digits to represent it. Is that okay? All right. So who wants to write numbers in binary? Just imagine all your math homework, linear algebra, calculus, and whatnot, everything that needs numbers. And the professor says, I want you to use binary numbers. Well, the conversion process is not too painful. The painful part is handwriting those digits on a piece of paper because there will be a lot of digits. So that's why we go like, oh, okay, that's not handy. So we go like, well, maybe we should switch back to base 10. No, no, base 10 sucks. So you ask, why does base 10 suck? Okay, so before we address why it sucks, let's address why do we even use base 10? Exactly. We are used to counting fingers without, holding beer on one hand. So that's the only reason why we use base 10. Okay? But base 10 is not a really good base to use because how long did it take you to memorize the multiplication table? A while, right? Can you imagine the multiplication table of base 2? Let's work this out really quickly. I'll do it on the board. The multiplication table of base 2. You guys are looking at this and go like, oh, I get the point now, right? 0 times 0 is a 0. 1 times 0 is a 0. 0 times 1 is a 0. 1 times 1 is a 1. How long do you think it would take an elementary school person to memorize this multiplication table? You can teach this over lunch break. Done. Multiplication table? All done. All right. What about addition and subtraction, which we will actually get to later too? So in base 10, that's not easy either, okay? Because to understand that 5 plus 7 is 2 with a carry of 1, I'm just going to write it this way, 1 carry, a carry of 1, that took some mental exercise, okay? When you're like 5 or 6, this is not easy to understand, that you have just run out of digits to represent the quantity. That's why we have a carry. When you're subtracting, you have a borrow. Same concept. Okay, you're subtracting, the actual quantity is negative already, so you go like, oh, okay. So it's going to be this number. Okay, so if we reverse this, 5 minus 7 is a 8 with a borrow because the borrow is borrowing a quantity of 10, so it's a borrow. So you have a borrow. This table is big as well. Okay, addition is not too bad because it's symmetric, but subtraction is not commutative, so you still kind of have to remember a lot. So let's take a look at binary. Binary says 0 plus 0 is 0 with no carry. 0 plus 1 is 1. Are you sure we can represent 1 in base 2? And it has no carry. 1 plus 0 is 1 with no carry. The only one that is tricky is 1 plus 1. It is a 0 with a carry because you cannot represent 2 with a single digit in base 2 because all the digits that you have are zeros and ones. Okay, fine, that one is a little tricky. But still, look at this the size of the table. Basically trivial. Okay, so getting back to why base 10 sucks, because base 10 requires a large multiplication table. Addition and subtraction also require a lot of memorization. Okay, then you go like, but tech, that is not solving the problem that we had, which is base 2 requires a lot of digits. Okay, we don't want to have to write a lot of digits. So how are we going to get around that problem? Well, in addition to base 2, we also have base 8, okay, octal numbers, where sober octopi would use. We also have base 16, hexadecimal numbers. We also have base 64 numbers. Okay, if you're into networking, that sort of thing, then you will also know that base 64 is a fairly common thing because HTTP as a protocol is an ASCII protocol, which means it cannot express things in binary. So that means if you have like an image that you want to transmit over HTTP, you cannot just transmit the bytes as is. Everything has to be converted into ASCII code before they can be transmitted. So the most efficient way to convert a binary file into ASCII code is base 64, so that you convert an 8-bit binary number to okay, that's not the way to say it. Each character can express a single digit in base 64. So you do lose some efficiency, but it's not quite as bad as some of the other bases. So we do have base 64. So what is common between these bases that I just mentioned? Base 2, base 8, base 16, and base 64. What is common between all of those bases? They're all powers of 2. As it turns out, when you're converting from base 2 to base 16, for instance, you don't need multiplication, you don't need division, you don't even need comparison. You just look up a table because 16 is a power of 2. The same applies to base 64, base 8, and so on. And it's bidirectional. If I give you a base 16 number and I ask you to convert it back into a base 2 representation, it's just table lookup. Are we good so far? Okay, are we understanding why base 10 sucks and that there are many alternatives that we can use? If I were a politician, my platform is going to be, let's reform the number system. Instead of using base 10, switch to base 2 or base 16. That would be my platform. So I think all of you here will vote for me, but that's about all the votes that I'm going to get. All right. Well, are we doing okay so far with base conversion? All right. So now is a good time to go back to the notes because all the notes has captured is really the same thing that I have already talked about. Okay. With some minor adjustments. So the minor adjustment has to do with how do we convert things? Oh, this is not showing up well. I have no idea what just happened here. Darn it. No, it's just I think it's a hiccup on the other side. On the browser side, maybe the connection just kind of dropped or something. I don't know, but it's fine now. So this part we have talked about already. Okay, breaking up a number into a summation of a coefficient times the base raised to a particular power, and the power is location dependent. So that's why we call the 6 digit 0, the 1 is digit 1. And can anyone tell me what is the 3? It is a digit, okay? Look at the pattern. Digit 0, digit 1. This is on the other side of the 0, is digit -1, okay? The 3 is a digit -1, digit -2, digit -3, and so on. Are we good so far? So then, this is what I often do in this class and my other classes. Then we generalize. We look at the pattern, and then we go like, okay, we can work with one concrete number like this, but we can express it like this, okay, into a very general pattern. So in this case, D0 is digit 0, D1 is digit 1, D negative 1 is digit negative 1, and so on. So the paragraph on top of this explains the notation. Okay, I'm going to focus on just exactly where it says that. So now we use the notation D subscript I to represent the digit that indicates the quantity of 10 raised to the power of I. So this is abstraction. In other words, I am coming up with a notation to express something in general instead of just pointing to a specific digit and say, oh, this is digit 1 and this is digit negative 5 and so on. I just come up with a name, a convention to name each digit in a number, in this case in base 10. Are we okay with that concept? Okay. So if I want to figure out what value a number is representing, then it's really just a summation of all of these things, just like what we did over here. The value being represented is the summation of the coefficient, the d of something, times 10 to the power of the position of the digit. So that's why I come up with this term over here. Does everybody understand what the sigma notation is representing? You good with that notation? Okay, it's summation, right? So in this case, we are adding together where I goes from negative infinity as an integer to infinity as an integer, d of I, so whatever digit is at place or location I, times 10 to the power of I, and that's when you add up all of these things, you get v. So I'm going to pause a little bit here and see if there are any questions about the notation and the process of abstracting things, the process of making things more abstract, less concrete, so that the pattern can be reused in a more useful way. So we're good with that? Yes, go ahead. Yes. Well, just because, okay, so let's take a look at 16.375. Okay, I'm going to put this on the whiteboard. 16.375. So it looks like the digits should only range from -2 to 1, right? Because this is digit 0, this is digit 1, digit -1, -2, and sorry, -3. Okay? So it looks like the range should not be going from negative infinity to positive infinity. Well, let me ask you this question. Can I put a 0 here? Can I put a 0 here? Can I put in like until the ink runs out or I run out of board? I can add as many zeros as I want on the right hand side to extend quote unquote the number, as well as on the left hand side, I can also add as many zeros as I want. So that means this particular number intrinsically has an infinite number of digits. It's just that only 5 of those are non-zeros. The rest of the digits that I don't even bother to write down, they're all zeros. So that's why I use negative infinity integer to positive infinity integer because ahead of time I don't know the number of significant digits. So that's the reason. So is that addressing your question? Excuse me. Okay. Well, I mean, you can take your time if you want to reformulate the question because I might not have understood the question myself. You good? Okay. All right. So that's one conversion because if you want to if a yes, go ahead. Mm-hmm. Yep. Correct. Yep. So I think your interpret so the So the reason why I bounce around here is because your addition is commutative, which means the ordering is not important. As long as I have the one and the -1, the two and the -2, somewhere in the addition, it is coming up to the same summation, the same actual value. Mhm. All right. So this is the equation that you need in order to convert from a non-base 10 to a base 10 representation. Because in general, if I'm given a base 7 number from, if a drunk octopus give me a base 7 number, how can I modify this whole thing in order to deal with base 7? Exactly. Replace all the 10s with a 7, right? So that means, oh, so in the final sigma form, whatever this 10 is taking the place of, that's just the base. If I'm dealing with base 7, just change the 10 to a 7. If I'm dealing with base 2 or binary, change the 10 to a 2. If I'm dealing with base 16, change the 10 to a 16. Oh, so we can use another level of abstraction, which means, oh, let's get rid of the useless detail because this formula works for any base. As long as b is an integer that is greater than 1, it's going to work. Are we doing okay so far? Okay. So this is the typical way that I try to explain something is to give concrete examples that is so trivial. You would ask, why are we even talking about this? And then I will let you look at the pattern, okay, to kind of abstract it, and then abstract it a little bit more, and then abstract it even more until we get to the point where, oh, this is the essence of what a number is, regardless of the base. All right. So the other way around, which is converting a value into a particular base, this is the equation that you can use. It's a little bit clumsy, but it is a very easy way to do it. V is the value that you're given with. P is the base. I is the position of the digit of di. And then this symbol is called the floor operation. The floor operation, I'm not sure whether I explained that or not. Okay, let me just look for the floor. I did not. Okay. So the floor operation is okay. So if this is new to you, you can try to write it down. Okay. So the floor of x being a real number, is the largest integer that is less than or equal to x. That is how floor is defined. And the symbol that you saw earlier, it looks like a square bracket, but missing the top. That is basically the same thing as saying floor. It's a mathematical notation. Uh, we're talking about math. No, it is the largest. It's the largest that is less than the value. Okay, so let's plug in some numbers, okay? Because so whenever you feel that, okay, this is a little bit too abstract, I have no idea what this is, plug in concrete numbers to make sense of it. Okay, it's a really useful technique. Okay, whenever something looks too abstract, and you go like, okay, I cannot read this, but I can try to figure out this. Okay, so now I'm asking, what is the largest integer that is less than or equal to 2.3? What do you think? It's 2, exactly. So 2, in fact, is the largest integer, but still less than or equal to x in this case, which is 2.3. Okay, so I'm going to ask you a trickier one, which is the floor of negative 1. Let's make it 1.67. Okay, so now we're looking at the largest integer that is less than or equal to negative 1.67. So what is that? Hmm. So is it -1 or is it -2? It is not -1 because -1 is not less than or equal to -1.67. It is -2. So that means floor is not the same as truncation. Truncation means you just get rid of the all the decimal places, but floor is trying to shift it. It's trying to kind of in modern day terms, it's called snapping, right? It's snapping always to the left hand side. Ceiling is always snapping to the right hand side on the number line. All right. Okay. So now that we have floor, let's check out the equation here. This is the general equation. So we're going to use the drunk octopus example again, okay? Because we already know all the digits, so we can work that out. So if I remember correctly, V is 206. And let's just say we want to work out the 1, okay? So we want to work that out. So now I can kind of put this on top of this, and we'll try to work it out. So we say V is 206. B is 7 because we're dealing with base 7 in this case. And I is 1 because I'm trying to figure out digit 1. So this method is kind of clumsy. It can only work out one digit at a time, okay? But from the other perspective, it's easier this way because you just have to kind of do this for each digit and you have the whole number. So now we try to do all the calculation, which is taking the floor of 206 divided by 7, which is B, to the power of 1, which is I, take the result of the floor, and then mod, which is the percent symbol here, with 7 itself, okay, because B is 7. So let's try to do this calculation. 206 divided by 7 is, okay, it is 2, so that was 66. 66 divided by 7 is a 9. Yeah, I think so. And then we have a mod with 7. So that would, oh, okay. Actually, I need to give you the full number here. It's not just 9. Let me get a calculator because otherwise I'm not showing you what the floor is doing. So let me do the actual calculation. BC scale is 5. We're trying to calculate 206 divided by 7. There we go. So it's 29.62837, blah, blah, blah. Okay, so we'll just take a few of those digits. 428. Okay, 428, blah, blah, blah. Okay, there we go. So now we take the floor. Okay, so in this case, because the number or the value is non-negative, so floor is the same thing as truncation in this case. So it's just 29 here. 29 mod 7 is the remainder of 29 divided by 7. That would be 1. So do you guys remember the actual base 7 number? What is in digit 1? I only have to scroll up. Okay, so this is also a really good moment to talk about note taking because to answer the question that I just asked, and you go like, oh, wait, yep, I got it in my notes. Congratulations, you are taking notes the right way. Okay. On the other hand, you go like, I have no idea. Then you might want to consider taking notes. Okay. Note taking is important not because, well, Tech, you think it's important only because when you went through college, you have to take notes. We got technology now. We don't have to take notes. No, it is not because of that. It is because my brain works about the same as yours. My short-term memory only is about 20 seconds. So is yours. That part has not changed because, I went to college. Like, I have to do some math to remember when I went to college. 85. So that would make it 40 years. Okay. Um, it has nothing to do with those 40 years. It has to do with biologically, physiologically speaking, your short-term memory is still short-term. So that's why we take notes. All right. So anyway, getting back to the example earlier, it was 413. So I got the one back correctly. It is one is digit one in the base 7 representation. So why is this kind of exercise important? Because you can find built-in exercises within the reading material by questioning, is this method working? And you just go like, okay, let me reverse, the whole operation and see if I got back what the other part is figure out. You are reapplying what you have learned, but in the opposite direction, so that it's better, you get a better understanding of the concepts and the material by doing this. Okay. Identifying things that you can do while you are reading the material is a really helpful thing, because most of the exercises at the end of a module or chapter in a textbook, many of those are very chore oriented. They're tedious. They ask you to do the same thing over and over again, just with slightly different numbers. That's not going to help you in terms of understanding the material. Identifying things that you go like, okay, did I have I learned enough to try to reverse this operation or to double check this is actually correct? That constant questioning of, can I do this? Can I double check these things? Can I apply this to the things that I have already learned and so on? That is going to help you. It's going to help you in the long run. But since we are 40 years from where when I went to college, now we got this, which is a terrific resource, and at the same time, it is a terrible resource. It depends on how you use it, just like a chainsaw. So now you can say generate some questions from which module was that? 0820. So I can check whether I understand Bayes conversion. Okay, first time I actually did this. Okay, so we'll check out your ChatGPT. Does it actually do things correctly? Conversion practice. Convert the decimal number 37 to base 2, 255 to base 16, 110, 101 back into decimal, and so on. Okay, cool. And there are these are also conceptual questions that you can answer. So what I'm going to do, as usual, is I'm going to try to trick ChatGPT and give it the wrong answer. Okay, so let me pick one, to do it in the wrong way. All right, I'm going to pick number 8. Okay, the binary number of 110101. The correct answer. Okay, so let's talk about the correct answer first, and then I'll mess it up and then see if ChatGPT fixes that or detect that. There's one of one, none of two, one of four, 0 of 8, 1 of 16, and 1 of 32. Are we all understanding why I said what I said? Because each digit tells you the number of 2 to the power relative to the position of the digit. Is that okay? So if this is kind of like the first class where you have to deal with base 2 numbers, it might be handy that you keep track of all the powers of 2, because it may not be natural for you to remember all of those. So just jot down on a piece of paper a post-it, okay? And just go like, okay, 1, 2, 4, 8, 16, 32, 64, 128, and so on. Okay, before long, you would remember those. Okay, it's not really that hard to remember once you use it a lot. So in this case, question number 8 is, this is 5, 5 plus 48 is 53. Okay, so let's just say that I missed one of the powers of 2. So 53, let's say I missed the 4. So that will make it what, 53 minus 4 is 49. Okay, so I'll say 49. Okay, the answer to question number 8 is 49. So I intentionally make a mistake and see what happens. Good try. Okay, and it says step-by-step conversion. Okay, the rightmost digit tells me the 2 to the power of zeros. The next one is 2 to the power of 1, 2 to the power of 2, and okay, so it shows you the correct answer and the steps to do it. And it even says it guessed. Okay, what is the term? Sorry. No, it's extrapolating, right? It is extrapolating what I did wrong to get the wrong answer. And it was right because I specifically made that particular mistake of saying, oh, let's just say that I forgot to add the 2. It even extrapolated from the answer that is wrong. It even told me what I did wrong to get to the wrong answer, or what is most likely that I did wrong to get to the wrong answer. So you have access to this kind of tool now, and I would say use it. Okay. The right way to use this kind of tool is when you're studying, when you're trying to understand the material. Okay. It is a good way to use the tool, but do not rely on the tool in an assessment because well, in this class it's almost impossible because all the tests are in person, on paper. Okay. And no electronics is allowed. Okay. So I just let you know ahead of time so there's no surprise, right? But generally speaking, in terms of college, the things that I want you to have competency on, even though you would say, but the computer can do the base conversion, much faster than I can. What is the whole point of asking me to show you that I know how to do this? What do you think? Why is there a necessity for me to know that you know how to do it, even though you may not be as fast as ChatGPT? So that you know why it's doing it, how it's doing it, so that when the computer gets something wrong, you can tell that the computer is wrong. So this is elementary stuff when it comes to computer science. Okay. So when people vibe code, do you guys know what is vibe coding? Have you heard of that term? No? Okay, so people who have not heard of these terms, I would recommend you to check out certain websites that can keep you up to date on technology stuff because you really need to know where things are, where things are heading, what you need to know, and so on. Okay, because you don't want to be surprised by the time you graduate. Okay, so I'm just gonna ask, what is vibe coding? Okay, so Google usually does an okay job with a kind of surface explanation. So vibe coding is a software development approach that uses large language model LLM to generate code from high-level natural descriptions rather than manual coding, blah 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 blah. So for the most part, you can think of this as people who have not gone through the computer science program for one reason or another, using AI, they can now they think they can write code. I have this great idea of how to keep track of exercises and calories, from gym, from the time people spend in the gym and what they do in the gym. But I know nothing about JavaScript or any programming concepts. But I really think this app is going to sell. So in the past, people would have to hire a software developer, tell the developer, this is what I want to do, and then the developer would charge some money, and then the person who came up with the idea would go like, oh man, I didn't know it's going to be that expensive, and so on. And these days, you can probably just kind of have the app to have the AI to generate the app for you. Well, the problem is people who do that may not have a good understanding of computer security or scalability. Okay, the code may only it may work in the sense that every end user would use the same database. So they're all cross-referencing each other's, gym activities. Like I didn't go to the lab yesterday, but according to the app, you did, because all users are actually using the same database, the same table on the internet without the structure to deal with multiple users. So all of these things that actually require a certain expertise to account for, the person who's doing the vibe coding may not be able to specify those really critical things. Okay? So how does that fit in this conversation? So does that mean people should not vibe code? That is not what I said. Okay? What I'm really saying is if you already know how to do something, okay, it's going to take you 2 weeks to do it, but you know how to do it. You know how to check whether it's doing the right thing or not. It will take you 2 weeks. And you know this tool, if you give it the correct input, the full specification of what the program is supposed to do, it can get it done in 5 minutes. I would say do it. Okay. And then after 5 minutes, you're going to spend, I'm going to say 2 days to go over the code that the AI generates and and then test the code, right? Interact with it, test it, push the boundaries, test for security concerns and whatnot. Okay. It might take you 2 days, okay, which is not terrible. You're still saving time. The app that comes out is still working the way it's supposed to. So this is good. Okay. So I'm not saying no to vibe code. I'm basically saying not everybody should vibe code. You still need a computer science degree, have a competency to write the code to begin with in order to make the most out of AI generating the code. Are we good so far? Because I know someone who's doing quote unquote vibe coding. He's inventing his own programming language by only vibe coding. And I have no problem with this guy doing it at all because he has a PhD in electrical engineering and also computer science. And where his job is working at Lawrence Livermore National Lab, it also requires expertise in mathematics and also physics. So with his background, I don't have a problem because he knows exactly what the program needs to do, what it is not supposed to do, and he can basically review the code that the AI generates in a short amount of time and make sure everything is all good. This is important to you because this is one of those things where you can go like, okay, I think I'm starting to understand what I can do that AI cannot do because the the, the clock is ticking. To most people in this class, you have about 2 to 3 years to figure out what you can do that AI cannot do. So, what is the best way to approach that? I know I'm digressing a little bit here, but I think this is an important digression. How do you figure out what you can do that AI in general cannot do? What is the first step? Hmm? You have to learn how to code. Exactly. Figure out what AI can do and figure out what you can do. But how do you figure out what AI can do? You have to be more specific. Okay, what AI are we talking about? Are we talking about LLM, GPT technology? Are we talking about stable diffusion? Are we talking about, you have to know what technology you're talking about. Let's say we're talking about GPT. Okay, GPT stands for Generative Pre-trained Transformer. Okay, what does that mean? Look into it. Okay, Now, I do have to warn you, okay, to fully understand, a GPT mechanism, you have to a an understanding of linear algebra will help. Okay, I'm gonna have to say that. However, the general way that the GPT works, what is a context window in the GPT, that you really don't need to use a lot of math. But you do have to understand the why the size of a context window is important and why that intrinsically is going to limit what GPTs can do, regardless of whether it's coding or processing long documents and whatnot. Okay, so know the details. Okay, spend the time to understand the technology, at least to the point where you can make a conclusion of, okay, so according to this, GPT cannot handle really large code base because the entire code base cannot fit into the context window. That is an intrinsic limitation of GPT when it comes to coding. It just cannot handle it. Okay. So now you have to go like, okay, so how large of a program can GPT handle? Well, how many tokens can the context window accommodate? Depends on the LLM that you're working with. It can be as limiting as 8,000-ish, tokens, which is a really small program, all the way to, I'm gonna guess, around 200,000 tokens. So the ratio between number of bytes of a file to token is about 4 to 1. Okay, so you divide a file size of the source code by 4. That's a general guesstimate of the number of tokens. So now you can kind of have an idea of how big of a code base um, the AI can handle. So that means, oh, okay, for smaller programs it's okay, but for larger programs it is not okay. And then the next question is, what is the context window? What does it do? So this is the one thing you can take away. The next token or the token or the word, the next word that GPT comes up with is entirely dependent on all the words from your prompt and its responses to your prompt. So that whole history of the conversation dictates what next word is going to come up with. So that means if you have an app and you want your ChatGPT to write it for you, if you don't specify enough details, context, constraints, specifications, and whatnot, ChatGPT will not be able to take that into consideration. So that means the entire context, everything that you need to specify, they all have to be in the context window in order for GPT to have a chance of generating the correct code. What you did not specify may be implied. GPT may make assumptions, but it may not be making the correct assumption. Okay, so I think that is important. Okay, because it means you can use vibe code, you can vibe code, but only if you know what you're doing, what the tool can do, what it requires to get the job done correctly. So I think those are all pretty important stuff, for you to become uh, the next generation of software developer and make use of AI to make your job more efficient. All right. So did I just waste 10 minutes of your time? I hope not, because I don't want to give you guys refund. All right. Well, we do have a lab today, which is going to be pretty easy, because it's based on the lab from before. It's an extension of the lab that you did the other day. So I'm going to expose the lab for today now. And it does have a access code, and this time it is Nandroid. I like puns. All right, so I'm going to write the word Nandroid on the whiteboard. Now, for people who did not get the previous lab done correctly, um, I suppose I can work this out. so that you have a good starting point for this lab. It's not reliant on your previous one. If you get a 1/1 from your previous lab, you can just use that file to as a starting point. Okay, that'll be good. Yes. Or I can just work on it and send it to you before noontime. Do you think I can do it? Let's see. Let's see. Logisim. All right. So this would be a good review of how to use Logisim. So even if you, especially if you did not end up with a working NAND gate from last time, this would be a good exercise. So the first thing I do is I use an input pin, turn it into 8 data bits because that's what the question asked for. And then the output pin is going to have 8 data bits too, and it's going to be the output. And then in between, I just need to create the circuit. So I'm going to need power. I need ground. I need 4 transistors. So I need 2 of the P-type transistors. I'm going to flip both of these to face south. One of them I can make it flip the gate position just so that it looks nicer. And put it here, put it here. And then I need 2 N-type transistors. So I duplicate these 2, put here. I need these to face north, and they are both N-type, like so. And depending on how you want it, I am going to flip the gate position of this one. So some people made the mistake of not using N-type transistors below, and some people might have made a mistake of the direction of the flow because it always has to go from source to drain. And for N-type transistors, the source is pointing to ground, and for P-type transistor, the source points to power. The trickiest part of this circuit is how to construct the splitters. So now I'm ready for the splitters. So to do the splitters, you need to pull a splitter out of here. A fan out of 2 is fine, but I need to have 8 data bits because the merged end is going to have to connect to the input pin. So that's why it needs to be 8-bit wide. Out of the 2 outputs, only 2 should be in use, or only 2 of the bits should be presented, 1 to each split end. So this is good. This one needs to go to the, oh, this one needs to go to the bottom. And then everything else should be none because I have no use of bit 2 all the way to bit 7. Like so. There we go. And then the top one, now this part is not crucial because the NAND operation is commutative. So it doesn't really matter, whether bit 0 go to these 2 or bit 1 go to those 2. You can kind of take your pick over there. And now I just need to bring this one around to the other gate over here. And then for the output pin, I also need a splitter, but this is going to be a strange looking splitter. It's going to have to face west because the merged end is connecting to the 8-bit output pin. There we go. And I need a fan out of 1 because I only need 1 single bit connecting to bit 0 of the entire thing. So everything should be off because only bit 0 is actually utilized. So all of these are off or none. And this just connects to the only split end over here, and that's the circuit. And then I switch to the appearance view, make sure it looks okay, and now I can save it. All right. So what I'm going to do for people who did not get the lab done correctly on Monday is you can go to announcement, and I'm just going to put this into the announcement so you can download it. If you got this done already correctly, you don't have to use this one. You can use your own. So now we switch to announcement. And put it as an attachment. There we go. Publish. All right. So everybody has a starting point now. Hmm. Okay. All right. So it does tell you where you can find the description of that. So let's try to follow that, which is the guide to being a Logisim user, and you want to look in attribute. Yep. Yeah, I think it's under two. Okay. It's one particular portion of the screen, but I cannot remember which one. I think it's this portion. All right. I'm stopping the recorder and have it uploaded.